Section 1. Introduction. In this introduction, we discuss the challenges of training language models, LMs, in specialized fields of knowledge. The main issue is the difficulty in accurately labeling data in these areas, which can be time-consuming and prone to errors, especially when specific expertise is required. For instance, even PhD holders and students can make mistakes in highly specialized physics problems. As more natural language processing, NLP, benchmarks focus on domain-specific tasks, it may become increasingly difficult to obtain large human-labeled training datasets for these tasks. This issue is part of a broader problem known as the scalable oversight problem, which involves providing a good reward signal to a model when it's hard to determine if its outputs are correct. In this paper, we explore the concept of easy-to-hard generalization, which is crucial for understanding how challenging the scalable oversight problem is. Easy-to-hard generalization refers to how well a model performs on difficult test data when it has only been trained on simpler data, based on a human measure of difficulty, such as grade level. Given that collecting training data in advanced fields like graduate-level STEM is costly and time-consuming, it would be beneficial if we could enhance model performance in these areas by only training models on cleanly labeled data from simpler domains, like high school STEM questions. To evaluate how well current LMs generalize from easy to hard data, we train models on easy data and test them on hard data, then compare them to a model that has access to labeled hard data for training and a model that is prompted to answer questions without any training. The final metric we're interested in is the supervision gap recovered, SGR, which measures the performance of a model trained on easy data, hard data, or no data at all, on hard test data. This metric is 100% when training on easy data is as effective as training on hard data, and it is 0% when a model trained on easy data performs no better than a model prompted without any training. Our main finding is that models generalize quite well from easy to hard data, often performing almost as well as a model trained on hard data. In experiments with various datasets, we find that the supervision gap recovered is usually between 70% and 100%, meaning that training on easy data is at least 70% as effective as training on hard data for hard test performance. These results are consistent across different model scales, hardness measures, datasets, and training methods. Our findings suggest that current LMs generalize well to unseen data across different levels of difficulty, even when trained on data that is measurably easier than the test data. This implies that training on easy data may be more effective than training on hard data when it's possible to collect more easy data within a given budget, or when easy data can be labeled with lower error rates than hard data. We also aim to understand how easy-to-hard generalization changes with model scale and the gap between training and testing difficulty. We find that the supervision gap recovered is highly robust across model scales, and that easy-to-hard performance may start to decline when the gap between training and testing difficulty becomes too large. The rest of the paper is organized around the following research questions. 1. How can we measure data hardness? Do different approaches agree? 2. Can we perform well on hard data by training on easy data? 3. What are the cost-benefit trade-offs of collecting easy versus hard training data? 4. Is easy-to-hard generalization consistent across model scale and the gap between training and testing difficulty? We summarize our main conclusions as follows. 1. Our 6 human hardness measures and 1 model-based measure are empirically diverse, and model performance declines on harder test data for each measure. 2. LMs generalize surprisingly well from easy to hard data, closing 70% to 100% of the performance gap between a model prompted without any training and a model trained on hard data. 3. It is often better to train on easy data when hard data is more expensive to collect or has noisier labels. 4. The supervision gap recovered is highly robust across model scale. Easy to hard performance may start to decline when the gap between training and testing difficulty is large enough. Section Summary. In this section, the authors discuss the challenges of supervising language models, LMs, in specialized domains due to the difficulty of correctly labeling data. They propose the concept of easy-to-hard generalization, where models trained on easy data, e.g., high school STEM questions, perform surprisingly well on hard test data, e.g., graduate-level STEM problems, closing 70% to 100% of the performance gap between unsupervised and hard-supervised training. This finding suggests that training models on easy data can be more effective and cost-efficient than training on hard data in certain scenarios. Section 2. Related work. In this section, we'll be discussing the concept of curriculum learning, compositional generalization, and easy-to-hard generalization, as well as how we measure the difficulty of data points. Curriculum learning is a method that has traditionally focused on how models perform on challenging data points. It's been suggested that starting with simpler data can help models later learn more complex concepts, thus improving their performance on difficult data. However, some studies have found that starting with difficult data and then moving to easier data can also be effective. Our goal is not to optimize the order of training data, but to explore how well models can generalize from easy to hard data. Our findings indicate that pre-trained language models can generalize quite well from easy to hard data, which could reduce the need for heavily engineered training curricula. Compositional generalization is another area of study that has shown that neural networks often struggle to generalize to problems that require combining reasoning steps in ways not seen during training. Some research has started to identify the conditions under which models can generalize to more complex problems. For example, transformers tend to perform better on algorithmic problems that can be solved using a specific type of program. However, even advanced models can struggle with simple mathematical problems that require more reasoning steps than seen during training. Our findings align with these studies, showing that models often perform worse on test data that requires a higher number of reasoning steps. Easy to hard generalization is a concept that highlights the challenges of providing a proper reward signal to a model when it's difficult to assess if its outputs are correct. Evaluating this type of generalization can provide useful context for understanding the difficulty of scalable oversight problems. Previous work in this area has shown that models perform worse on reasoning tasks when trained on easy data rather than hard data. In contrast to these studies, we found that in many cases, easy to hard generalization is comparable to hard generalization. To measure the difficulty of data points, we need to distinguish between easy and hard data, based on human ability to correctly label the data. We've identified several factors that can make problems harder, such as requiring specialized training and knowledge, taking longer to solve, causing uncertainty about the final solution, and requiring costly or noisy methods to obtain the answer. We've developed specific measures to capture these factors, including the level of education needed to answer the question, expert ratings of difficulty, required cognitive skills, question length, answer length, and the number of reasoning steps involved. We also use a model-based metric to measure the difficulty of data points. In our experiments, we used 4 datasets that contain annotations for some of these measures. These datasets include U.S. grade school science questions, domain-specific multiple-choice questions for various subjects, general knowledge trivia questions requiring compositional reasoning, and U.S. grade school math word problems. We found that there are generally fewer hard data points than easy ones in our datasets, given the relative difficulty of collecting hard data. Section Summary. In the section, 2 related work, the authors discuss previous work on curriculum learning, which focuses on the order in which models are trained on easy and hard data. They also mention studies on compositional generalization, which explores how well models can generalize to problems that require combining reasoning steps. The authors aim to investigate how well models can generalize from easy to hard data and compare it to hard generalization. In the section, 3 Measuring Data Point Hardness, the authors describe various measures used to determine the hardness of data, including education, grade level, expert rating, required cognitive skills, question length, answer length, and the number of reasoning steps. They also introduce a model-based metric called minimum description length, MDL, to measure data point hardness. Section 4 Experiment Setup. In our experimental setup, we used Llama 2 base models of different sizes, 7B, 13B, and 70B. We also tested an RLHF version of Llama 2 to 70B, Qwen 72B, and Mixtral 7x8B, and found that the results were consistent across all models. We divided our datasets into 3 categories: easy, medium, and hard. This was done based on certain criteria. For instance, we used the 30th and 70th percentiles of the variable range to define easy and hard cutoffs for variables like the number of words in a question, the number of characters in an answer, and the MDL. Other variables were manually defined. For example, in the ARC dataset, we classified grade levels 3 to 5 as easy, 6 to 7 as medium, and 8 as hard. Similarly, we classified difficulty scores and Bloom skill levels. For the MMLU dataset, high school level was considered easy and college level was considered hard. For strategy QA and GSM-8K, we classified the number of reasoning steps required to answer a question. We used 3 different training methods: in-context learning, linear classifiers trained on frozen model hidden states, and QLORA. Strategy QA and GSM-8K benefited greatly from chain-of-thought reasoning, so we primarily conducted experiments for these datasets using in-context learning and QLORA, both combined with chain-of-thought reasoning. In-context learning involved placing training data into a prompt before each test question. We used 10 in-context examples for ARC and MMLU and 8 examples for Strategy QA and GSM-8K. For multiple-choice questions, we calculated the answer probability for each answer choice given the test input and the prompt. When generating outputs with chain-of-thought reasoning, we generated up to 100 tokens for Strategy QA and 300 tokens for GSM-8K, then parsed the string to get the predicted answer and calculated the exact match accuracy against the label. Linear probing involved training a linear classifier on frozen language model hidden states. This method is effective for multiple-choice question answering using language model representations, and it does not require any fine-tuning of the underlying language model. For each question, we computed one representation per answer choice by concatenating the question and answer choice and feeding it to the model. Then, we scored each representation by applying the linear probe. The answer choice with the highest score was returned as the prediction. QLORA is a recent method that uses low-rank adaptation of specific model parameters for extremely parameter-efficient fine-tuning of language models. We used the LoRa implementation from Hugging Face and the 8-bit Atom W from Bits and Bytes to fine-tune our language models. Model predictions were obtained in the same manner as for in-context learning. Our unsupervised baseline was zero-shot prompting, where we scored the answer choice probabilities given the question and took the highest probability answer as the model prediction. For the GSM-8K dataset, which does not have multiple answer choices per question, we used a simple, let's think step-by-step, style prompt. For all experiments with linear probing and QLORA, we used 160 training points. We would have preferred to use more training data, but we needed to ensure a fair comparison between easy to hard and hard to hard generalization, which required fixing the amount of training data and leaving enough hard data for testing. Despite this limitation, linear probing and QLORA showed good sample efficiency when applied to Llama 2 to 70B, so we were able to achieve comparable, and sometimes better, performance than in context learning across datasets. We performed experiments using 5 random seeds, controlling the training data selection and leaving the remaining data for testing. To obtain confidence intervals and compute p-values for comparing results, we performed a block bootstrap to combine test and train data variants. Section Summary. The experiment setup involved using different Llama 2 base models and conducting experiments on various datasets. The datasets were stratified into easy, medium, and hard data based on specific cutoff values. The models were trained using different methods such as in-context learning, linear classifiers trained on frozen model hidden states, and QLORA. Confidence intervals and p-values were computed using block bootstrap for statistical testing. Section 5 Experiments. Let's delve into the experiments we conducted to answer 3 key research questions. Firstly, we wanted to understand how we can measure the difficulty of data and whether different methods agree on this. To do this, we created correlation heat maps for the difficulty measures in our datasets. We used a method called Spearman rank order correlation to compare the difficulty values for each data point in a dataset. We used 2 datasets, ARC and GSM-8K, to cover all 7 of our difficulty notions. We found that our difficulty measures are quite diverse. The correlations between different measures were generally low, suggesting that they capture different aspects of data point difficulty. Interestingly, our model-based difficulty measure was quite different from our human-based measures. This indicates that it's important not to rely solely on model-based measures of difficulty. Our conclusion from this experiment is that we should assess generalization from easy to hard data using multiple human difficulty notions, informed by cognitive science. This is because several meaningful measures of difficulty do not strongly correlate with each other. Secondly, we wanted to know if we can perform well on difficult data by training on easy data. We tested models on exclusively hard test data, while varying whether they were trained on easy or hard data. Surprisingly, we found that our model, Llama 2 to 70B, showed comparable generalization to hard test data regardless of whether it was trained on easy or hard data. These results contrast with past work in curriculum learning and compositional generalization. This could be because the models we consider, like Llama 2 to 70B, have learned much more during pre-training than models commonly used in work on curriculum learning and compositional generalization. Lastly, we wanted to understand the cost-benefit trade-offs of collecting easy versus hard training data. We hypothesized that training on easy data might outperform hard data under two possible assumptions. 1. That one can collect more easy data than hard data given a fixed budget, i.e., time, money, and 2. That easy data is less noisily labeled than hard data. We found that there is often a clear advantage to fitting a model to easy data over hard data when the cost ratio between them is 1 to 2. However, for some measures, hard data does eventually meet or surpass the efficacy of easy training data. For the noise assumption, we concluded that it can be better to train on easy data rather than hard data, even when testing on hard test data. This is particularly true when the error rate for hard data is twice that of easy data. These findings suggest that there are plausible settings where it is better to train on easy data than hard data due to label noise. Section Summary. In the experiments, we measured the diversity of our hardness measures and found that they captured different aspects of data point hardness. We also discovered that training models on easy data resulted in comparable generalization to hard test data, suggesting that easy data can provide effective supervision for language models. Additionally, we explored the cost-benefit trade-offs of collecting easy versus hard training data and found that training on easy data can outperform hard data in terms of model accuracy, especially when considering factors such as cost and label noise. Section 5.4 RQ4. Is easy to hard generalization consistent across model scale and train test hardness gap size? In this section, we aim to answer two key questions that are likely to become more important as AI models continue to improve. 1. How does the recovery of the supervision gap change as we scale up the models? 2. How does the performance on difficult tests change as the difference in difficulty between training and testing increases? These questions are crucial because as AI performance surpasses human expertise in various areas, we need to understand if supervising these models will become increasingly challenging. To answer the first question, we examined the performance of three different sizes of the Llama 2 model, 7B, 13B, and 70B, on the MMLU dataset, using both easy-to-hard and hard-to-hard training methods. For the second question, we trained models on different levels of MMLU data, ranging from high school level to no training data at all, and then tested them on difficult MMLU data, which consists of college-level STEM questions. Our findings show that the recovery of the supervision gap is similar across different model sizes. For instance, the 7B model recovered 109% of the gap, the 13B model recovered 75%, and the 70B model recovered 97%. The difference in performance between easy-to-hard and hard-to-hard training methods was never more than 0.4 points. Regarding the second question, we found that the difference in difficulty between training and testing data can affect test performance. As the gap in difficulty increases, we observed a slight decline in generalization. However, even training on third-grade level data can be surprisingly effective for answering college-level STEM questions. For example, when training on 8th grade versus 3rd grade questions using ICL, the supervision gap recovered fell from 74% to 57%. These results suggest that while supervising larger models does not become more difficult, the performance on difficult tests may start to decline when the difference in difficulty between training and testing data becomes too large. Next, we discuss whether our tasks are challenging enough to provide generalizable results from easy to hard training. While humans can label all the datasets we use, the authors of this paper could not. As benchmarks have become more difficult over time, they now require specialized domain expertise. The largest difficulty gap we tested in this paper is between 3rd grade and college-level STEM questions. We also consider how language models can solve difficult problems with as few as 10 easy examples. Our results show that these models can efficiently learn to solve hard problems from easy data. This could be because this type of training encourages models to answer questions based on the truthfulness of the text, which should be consistent across different domains and levels of difficulty. Finally, we want to clarify that we are not trying to train models to answer questions for which there is no relevant information in their training data. Instead, we are trying to extract knowledge from models that we believe they may possess, using fundamentally weak supervision. This is why the performance on hard-to-hard training provides an upper limit for easy-to-hard generalization in our experiments. It would be interesting to consider how models perform on future data given training data from before a certain cutoff, such that easy data is from the past and the hard training data is relevant future data.